everyone. So this is going to be your PM2A2 workshop number 2. So workshop number 1 has already been done in class. This is obviously a little bit different now. We're going to do this as a sort of pencast online. Hopefully you've had a chance to look and have a go through the worksheet yourselves. So again, this is supposed to be used kind of retrospectively after you've had a go yourself. But again, if you had particular problems, you'll be able to work through them with me today. If you haven't seen the workshop and you're viewing this for the first time, obviously you can try and follow through the key points, and you should be able to see the worksheet on the screen anyway. So there are any key points that you can maybe help you work through some problems if you're seeing them for the first time. So this workshop was all about carbohydrate chemistry to start with, and then we come in and then we add a little bit from year 1 where we're actually dealing with isomerism, just to keep that in your minds in terms of the importance of isomers and the different types that we have. So this video will be split into 2 parts. Part 1, we're just going to be dealing with the carbohydrate chemistry side of things, and then in part 2 I'll deal with the answers for the isomerism section. Okay, so we'll get straight to it. So we have our learning objectives here. So the learning was really to practice a little bit about drawing. Carbohydrates, they're not always the easiest. Some of you will be more confident than others in terms of drawing and labelling structures, so it gives you a chance to practice a little bit about that. It will show you a little bit about how things are orientated in actual space and the importance of their orientation in terms of the reactivity and how they combine to form sort of larger carbohydrate structures. We need a little bit of mechanisms on how carbohydrates can interconvert. Again, it's important in terms of looking at the different properties of some of the different carbohydrates. And then finally, we're going to summarise some of the advantages and disadvantages of different synthetic methods of making carbohydrates. And it's important to think about the pros and cons of each of those different structures. In the second part, as I said, we're going to go on to a little bit of part 1, isomerism. So there'll be some examples of all the different types of isomers, just to sort of recap a little bit, as I'm sure some of you might have forgotten a little bit about isomerism and the importance of it, and actually, you know, how is DNL different from cis and trans, and all those sorts of things that you just need to refresh your memories a little bit. So we'll get to the first question. So the first question, hopefully if I zoom out a little bit more, we'll be able to see it as a whole. Okay, there we go. So this is all about a little bit about practice drawing. So you can try and recreate these in your workbooks if you want. The different types of drawing these structures. Again, remember things like bond angles and bond lengths are really important in terms of having an accurate structure or an accurate representation of our molecules. Now we've got a couple of different structures that we've shown you here. So these are actually the same molecule. Okay, so these are the same one, but we've demonstrated in 2 different arrangements or projections in this case. So this one is what we would call the chair form. And this one here is a Fischer projection. And in your lectures you've gone through those a little bit just to show you what they are and why we might use one over the other. Fischer projections are generally only really used for carbohydrates because it's an easy way to demonstrate orientation of the functional groups. A little bit easier than drawing it out in this kind of format that you see in the chair form. It's called the chair form just because it kind of looks a bit like a chair. If you can see that someone was sat at it here, really poor stick man, just in case, that's why it's called the chair form. I'll erase our little man over here. Okay, so the first question was starting you to actually play around with these structures a little bit and actually whether we can identify certain functional groups and their position and why it's important in their positioning. Lots of carbohydrates look extremely similar. So this structure here is galactose, and if you looked at the molecular formula, it's identical to glucose. But they differ in terms of where some of the substituents are positioned in the plane. Okay, so glucose won't look exactly the same as this. If you're interested, you can have a look at glucose, and you should hopefully be able to spot what the main difference is between glucose and galactose. Now these aren't the only 2 ways that you can sort of demonstrate structures. You also get Horwath projections as well, which are kind of commonly, you might be used to them a little bit more. They're kind of the way we would potentially normally draw a quick structure. Apologies, that bond is absolutely awful. My graphics tab doesn't always help me out sometimes. But that's what we would call kind of a Horwath projection, where we have all our our atoms arranged around the ring. It's kind of the easiest way to draw it, but isn't necessarily always the most accurate in terms of positioning of some of the atoms, because actually where they're positioned in space is really important in the difference between some of the different carbohydrates that we have. So the first question was using or applying conventions is to name or number, the carbon atoms in both of the structures. So that'll actually give you a chance to see actually can you correlate this structure, the chair form, to our F form over here, our Fisher projection, and can you see where all the carbons are in the structure? This is useful because we want you to start talking about structures or particular carbons in this sort of numbered format. Okay, so if you wanted to refer to this carbon here, I wouldn't want you just to say the carbon at the bottom left. I want you to say carbon, and we'll work out what number it is in a minute, but refer to specific numbers in terms of where you're referring to. And that's really important, in showing a slightly deeper knowledge of how structures are important or why they're important, and actually discussing them in the most appropriate way. Now this has gone through a little bit in your lectures, but again I can quickly guide you through how you would number this. So we always start the numbering from the anomeric carbon, so this is the carbon to the right basically of our ether group here. So in our ring format it's normally quite straightforward in terms of our numbering. So we always start here and then we work clockwise round the molecule to number all our other carbons. So remember our carbons are dotted in these points here. Hydrogens aren't shown in these structures, so just be aware that obviously we haven't just got 3 bonds, there is a hydrogen that isn't shown, and we'll actually deal with that a little bit later. So if you work clockwise around the molecule, this would be carbon number 2, this would be carbon number 3, we have 4 here, 5 is just in there, and then we have 6, which is just up there. Okay? So as I go back to before, if you wanted to discuss a particular carbon, you could say the reactivity at carbon 4, or you could say actually, the important one here is the difference between galactose, which is this molecule here, and glucose, is that in glucose, our oxygen isn't in this position, but our glucose, our OH, is actually pointing in this direction. Okay. So if you wanted to discuss the difference, you'd say the difference between the two carbohydrates is that in glucose, at carbon 4, we have a different position of our OH group. And it actually changes the properties quite drastically between glucose and galactose. Glucose is much sweeter than galactose, and it actually has a lower melting point as well. So even a simple change in their positioning, even though the molecular formula is still the same, can really impact the structure, or really impact its properties. And that's the importance of their positioning, and we'll probably talk about that a little bit later on. So the Fisher projection will look a little bit odd. It doesn't look anything like this. You might be able to spot where the carbons are. So the carbons are always at the intersects. So there's a carbon here, 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 and we've obviously got a carbon at the bottom, which is down here. And obviously these are going to correlate to the carbons that we have in our structure as well. Now we've got a ring open structure, so remember that carbohydrates, and again we'll come to ring opening a little bit later, we can open the ring of carbohydrates, and actually that will start to show us what this in reality means. So when the ring actually opens, what actually happens is that we lose this bond here, and we actually get a double bond formed. I'll redraw that because I can't draw in a straight line apparently. We get a double bond here, and then we can pretty much ignore this hydrogen, okay, because it actually gets taken off. And if you actually unravelled it, you could see that this double bonded oxygen attached to a carbon would actually be this double bonded oxygen attached to this carbon. So the Fisher's just opened the ring, okay, we've got rid of this bond here, and then we've shown where that double bond is now. So that actually makes it quite simple to start to see where the carbons are. This is the same as it was here, it's going to be our carbon 1. And as we did here, we went clockwise around the structure, we just go from top to bottom to number the carbons. So this would be carbon number 2, this is carbon 3, 4, 5, and then we have 6 at the bottom. Okay. So that's how you're going to number them, and again, the numbers are important because at each of the carbons we're looking at the position of our OH groups, and that'll tell us potentially the difference between the carbohydrates and maybe be able to look at the differences in properties a little bit. So it's important that you have that kind of down in terms of understanding how you would number, so you can use that numbering system when you're answering questions. Okay. So we'll move on now. So again, have a look at that. You can practice drawing these molecules out a little bit if you're not confident drawing a chair form. Fish is generally very straightforward, but again, it's good getting some practice drawing chair formations. Okay. So question 2 is looking about how the substituents on the ring are orientated in space. So you can see obviously we've got arrows pointing towards and away, so it's not a flat molecule, which is why we kind of don't use our kind of standard maybe ring representation that you might normally want to draw. This is why we use these chair formations, because it's actually much more, it demonstrates the molecule actually how it is rather than a kind of forced way that we've made just to make our lives easier to draw. So this is galactose again. Again, it's just the same molecule that we had at the top. So the first point is about drawing in the hydrogen atoms that we have. So quite often, and you won't normally see it with the hydrogen atoms drawn in, it's important to know that they are there, and actually their position is as important in terms of positioning as the OH groups. So always remember the carbon's going to have 4 bonds, so there's a hydrogen at each of these carbon positions. Okay. Again, important to pay attention to bond angles, and this gets you some practice in terms of knowing, when we have this kind of structural representation, how all the bonds are separated. You know that bonds will equally separate because obviously they want to sort of keep away as far apart from each other as possible, so the charge is sort of equalised or spread out as much as it can. But it's important that you're aware and are able to manipulate those. Now the reason why we don't often draw the hydrogens on is because it makes the molecule a bit messy here. They're not always particularly important, I suppose, in the reactivity of this carbohydrate when it reacts and binds to another carbohydrate, but it's still important that we know how to draw them in. So the first part of the question is about drawing the hydroxyl, not the hydroxyl, sorry, drawing the hydrogens in. And the second is looking at their sort of position in space. And we'd either label these as being axial or equatorial in their positioning. And again, when we start marking them on, I'll explain a little bit about what the differences is between those two. So if we go around the ring, we'll start at carbon 1, so hopefully you remember where carbon 1 is. Carbon 1 is just down here. Now to spread out evenly, we have a hydrogen that is directly down. Okay, now you can see why we don't add them in, because it goes straight through our H group here, which isn't a great way to represent it. Okay, but remember, this is how they're trying to spread out. If you'd actually done this in 3D space, these would all be equally spaced, because remember this is pointing towards the screen from behind, and these two are in sort of our normal plane, I suppose. So if we go around, I'll draw them in, and hopefully you have an idea of what this would be. So we've got another hydrogen just being placed there. This hydrogen is here. This hydrogen's over here. Now remember, if this was glucose, these would basically be swapped over, and that's what glucose structure looks like in comparison. I'll draw this one in here. I won't draw the ones on this carbon here because we're not actually too interested in this carbon in reality, but you could do if you wanted to. So hopefully your molecule looks something like that. Again, we wouldn't normally put them in there because it makes the structure quite messy, but don't forget that they are there. And we want to say whether these hydroxyl groups are in the axial or equatorial positions. So equatorial, basically if you think about planet Earth, we think about the equator runs around kind of the central plane of the Earth, okay? And that would be the equatorial plane in reality. It's anything that's lying kind of in a horizontal plane. So we call that E. Axial is the opposite, so if we looked at Earth, it would be from top to bottom almost. So you can think of that as a horizontal plane. And that's going to be our axial positions. And again, you might think of why this is important, but again, we want you to start discussing these groups in terms of where they are. So I wanted to discuss with you how this molecule is different from glucose or a different isomer of galactose. I want you to start to be able to use the correct terminology in terms of referring to the right carbon when you're numbering it, and then be able to refer to it as axial and equatorial, because quite often in isomers it's that's swapping over between them. So I'll go through and number them. Most of them are fairly straightforward, and remember, pretty much if you've got one in equatorial position, our corresponding H group is going to be in the axial position. So sometimes you might find it easier to denote just from this group, but actually sometimes the hydrogens give it away if you've drawn them incorrectly. So this bond here isn't completely horizontal, which sometimes confuses people a little bit, but remember this is in 3D space, so it gets a little bit more confusing in terms of how you actually see the molecule, but this is in the equatorial position. You could also have worked it out because this is pointing straight down, so you know that this is in our axial position. So you know that here they wouldn't both be in the axial position because again they're trying to spread out, so again that's how they're going to orientate themselves. If we move around, and this is probably the most confusing of them, you might think that this one is axial because again you think it's pointing directly down, but remember we have arrows here that are denoting that the molecule is going towards the screen at this point. So this is actually still in the equatorial position. Again, it would have given away, this is pointing straight up, so this is axial. Straight up or straight down will always be axial, okay? You won't get any sort of division in that. Move around to here, again, you'll see that this is going to be axial and equatorial. This is where they swap over here, so you can see that this OH group now is in the axial position, and this one is in the equatorial position. And for here, we've got this one pointing straight down, that would be axial, and this was equatorial. Even though you might think this is pointing straight up, in 3D space it actually isn't. And again, we've kind of used the glucose example. I'd expect you to say that we're dealing with a difference in the carbons, okay, 1, 2, 3, 4. So carbon 4 is where there's a difference, and the OH in glucose is going to be in the equatorial position, and that's its difference from galactose. Okay. So hopefully that gives you a chance just to see how to position all of those groups, and that the actual importance is their orientation in space, and that you can actually start to use your carbon numbering that you've learned or just demonstrated to work through that particular problem. So if we move on now to the second, almost part of the same question. So we come to isomers in the second part a little bit. So the structure we've actually shown above is beta-galactose, and what the second part of the question is asking you is to draw alpha-galactose. Now the importance of this is just to say that actually this is a monosaccharide, so this is just one not one galactose molecule, one carbohydrate molecule on its own. But remember, these chain together to make much bigger carbohydrates. So if you combine galactose with glucose, so if you joined via this oxygen here, a glucose molecule, you actually get lactose, which is a disaccharide. And it kind of builds in terms of that. You can get bigger structures of all different types of combinations, and they all have different properties based on those points. So you've probably heard a little bit about alpha and beta linkages with carbohydrates when we start combining them together, and that's important in terms of knowing the structure they form when they start to combine. For the moment we won't worry too much about this. I'm not going to go over that in particular depth, but you can go and have a look at that if you want to go over alpha and beta linkages with carbohydrates when they go from monosaccharides to disaccharides. This question is looking actually, and it's not a dissimilar problem to the one that we dealt with, our kind of glucose discussion, is that we have our beta galactose. How would the structure of alpha galactose look any different from here? Again, the question gets you to draw out a molecule, so please do draw it from scratch just so you get some practice here. I'm not going to do that just because it's a little bit more difficult for me to do on my graphics tablet, so I'm just going to get rid of some of our labelling so I can show you what the difference between the beta and alpha would be. So let's just remove this part of the molecule. Okay. So if you wanted to demonstrate what alpha galactose would be, it's all about the positioning of our functional groups. So if I draw the hydrogen as we have it in beta galactose, we have the hydrogen here. What's actually the difference between alpha and beta is the positioning of those two functional groups. So this one at this carbon and here. So what actually happens for alpha galactose, and we'll look about interconversions because it becomes important for carbohydrates. Oops, let me switch back to my pen. Is that this becomes our OH group, it's now pointing in the downward position, and I'll just cross out the oxygen, and now our hydrogen is in this position up here. And again, if you wanted to discuss it, you'd say that carbon 1, for alpha galactose, we have the OH group, okay, the hydroxyl group is now in the axial position, and our hydrogen group is in our equatorial position, okay? And that's how you would discuss it. Again, get some practice about drawing those two out, and it's really quite important that you get some of that practice in drawing those so you become more confident. But that's the simple difference between them. Okay, so if we move on to question number 3 here, and this is looking at, again, we spoke a little bit about carbohydrate structures and they can interconvert. We've seen the alpha and beta form. Is we actually want to show you mechanistically how that can happen. So in the question above we showed you that the two forms exist, but actually mechanistically under the right conditions they can convert between the alpha and beta forms. So the question is asking you whether you can actually fill in our curly arrows for the mechanism to get from our basically start form, which would be our alpha here, to our beta form down here. Now the question just asks you to deal with this specific box in the middle here. I'm going to go through the whole mechanism just so you can follow it through for sort of completeness, but it is there if you want it. But again, the question is only really asking for this particular point. So again, if you look at the start and the end, we can see this is our alpha form, and it converts to our beta form when we have under conditions of having a base in reality. So we're going to start drawing the arrows to sort of show how that conversion happens. As it's kind of given away already a little bit, it's done via a ring opening, so they can't just convert without this ring opening. This is the way that they do interconvert. And I'll show you a little bit about that mechanism and why it happens. Actually, it's a good practice for you to start to revisit that mechanistic plans and actually how they do combine and start to interconvert. Okay, so a bit of practice in terms of drawing mechanisms here, because there's a few key points that people always make mistakes with in terms of mechanisms. Okay, so we'll start with our galactose molecule. Now the first thing that I think is important for you to do is if you put your lone pairs, if it's going to draw, which it's not, 1 second, there we go, is if we put our lone pairs in our oxygen, actually that guides it a little bit in terms of what's going to happen. Now remember in terms of bonds and electronegative atoms, when we have a bond, the electrons of the bond will be drawn slightly more towards our electronegative atom. And you can remember things like putting things like delta negative and delta positive on bonds. These aren't physically charged this way, but the draw is there where the electrons are slightly more closer association with the oxygen than they are with this carbon. The same happens for the base in the OH, okay, so the H even. So the base is very electronegative, and we have our delta positive up here. And this kind of drives reactions in reality in terms of why things will happen. Without these kind of charges, things will be fairly stable as they are. We wouldn't expect anything to move around or this sort of conversion to happen. It's important that we think about what's happening here. Now, if you look at where we get from step 1 to step 2, you can see that it goes via, you can see what's happened here. We've got a positive charge in this oxygen. Now, you can just try and think about, in these questions, how do I get from this step to this step? But actually, if you deal with this and think, what will happen to this molecule, what can happen, you'll end up joining up to this step anyway. So, we have a lone pair here, or lone pairs. So there's some free electrons that can be available to react in certain conditions. And we have a delta positive proton here. So these free electrons, and remember the arrows always go from, are the movement of electrons, not the formation of bonds necessarily. So the electrons from our oxygen will be drawn towards our delta positive proton on our base. At the same time, so sometimes happens in this cascade, but you can think about this happening at the same time. The electrons from our bond here will go towards our base. Okay, so again, it's not showing necessarily where bonds are forming or breaking, it's showing the movement of the electrons. Obviously, this oxygen here has gained an extra bond, which obviously doesn't necessarily want to have in its sort of most stable form where it's neutral. But we have this bond here, which is why we get the positive charge. Our base has lost the proton, so it's gained a negative charge. Okay. So move on to the next step. The important thing to say here is that all these steps are reversible, and it all comes down to positioning of the different groups in space with each other. So this base down here is very close still to this hydroxyl group up here. Basically, it will interconvert in the reverse way, as we've just seen up there, back to our alpha galactose. Now obviously, things are always moving in flux in solution, so positions when this base down here is positioned much closer to our OH group down here. Okay. So when that happens, we're now going to have the long range effects of this hydroxyl group. It's now going to start to affect this hydroxyl group. So remember, we've got lone pairs on this hydroxyl group. We've still got a lone pair up here, but it's going to react slightly differently now. So the important thing to say here is you can think about your delta negative here and our delta positive. You can follow it through and you can see what's happening in the structure. But let's just think about what's going to happen. The ring is opened, okay, so we know there's been a bond change or bond broken here, and now we have a double bond forming between our oxygen. Now in the reaction, what actually happens is that the electrons from this bond between the oxygen and the carbon, electrons go to our oxygen to now neutralize that charge, and our electrons from this bond here go to form our double bond that we can see here. Electrons from our base now go and take our proton back, and that forms our structure here. Okay, so we've generated our base, we've opened the structure, and we've got our double bonded oxygen. So if you can follow that through a little bit. Okay. The next step to say is, you might think about why that's important, but remember, once the ring is opened, we can now have rotation around this bond. Okay, so this bond can now rotate round. Okay, so that's sort of designate rotation. And obviously now it can rotate in free space. So some positions, or sometimes, or certain aspects, it will rotate and it will be in our position that we can see in our next structure, where it's now in a kind of our equatorial position versus our axial that we might still sort of see here. And that allows us to actually allow the interconversion to happen, is when it is able to rotate around that particular bond. So we'll follow on to our next step to see actually how the ring recloses again. So the step between here and here is just saying at a certain point in time, this oxygen will be rotating around, and at a certain point it might be in a position where it's now in this orientation in space. And when the ring closes, it snaps it back shut in its new position. Okay, so I'll draw my lone pairs back in on this oxygen. Okay, we've still got lone pairs here as well. Not so important on this one, but we'll draw it there anyway, to show how the ring is going to reclose. Again, we're going to have a delta negative here and a delta positive here. So what actually happens is the electrons, or the lone pairs from this oxygen here, are actually drawn to carbon 1 to close the ring. At the same time, this bond will break. The electrons move to here. From here, now the electrons that we have will move to our proton. And as before, the bond or the electrons in that bond will move back to our base, okay, to get this structure here. Now there are two ways you can kind of do this. Is kind of the long-winded way of drawing it out, I suppose, when you see each of the steps in isolation. You can draw it slightly quicker if you choose, and you can just draw the electrons going straight from the double bond, breaking to form a bond with our proton, and again you'd still show the electrons moving here. Important here, the electrons, to close the ring, come from the lone pairs of this oxygen here, okay? Some people will draw it coming back from this double bond to close again. That isn't the way it happens, okay? There's nothing to drive that in terms of that, because remember our positive and negative sides are what's going to govern what happens with that molecule. So if I just erase a few of the lines that I've drawn here, either way of drawing that is absolutely fine. I'd accept either in an exam. Some people prefer this kind of slightly quicker view, but some of you will find it easier to follow the steps in terms of the electrons going to the oxygen first and then to our proton. So this gives us our structure here. Again, we've got a positive charge back on the oxygen, and we've got our negative charge on the base, almost back to where we were in this step up, in almost the second step that we saw. So obviously the last part of the reaction is to sort of reform and get rid of this positive charge. So importantly here, the electrons from the bond now go back to our oxygen, so we get the lone pair back, and our base is going to take our proton back to form our structures that we have here. So we've got our base reformed, and now we've got our newly formed galactose via the ring closing, but you can see that our position of our group, our hydroxyl group, is now in the equatorial position of the axial position that we had up here. So again, if you think about how it's going to bond in future, directional wise, in terms of adding more carbohydrates, it's going to go down in this direction, while it's equatorial, it's going to go horizontally potentially. And again, they have different properties and different reactivities in terms of how they move forward. So again, you might need some practice in terms of doing the mechanisms, but again, follow through the process of it always being the movement of your electrons that you're trying to show. Okay. So the final part of the question, or the final part of the workshop that we worked through, was just actually looking at the synthetic methods of making some carbohydrates, and actually what the advantages and disadvantages of sort of chemical synthesis over enzymatic methods. Again, I know I'm kind of jumping from topics a little bit, but remember your lectures go through each of these in sort of isolation and link some of the in-between points together, so please have a look at those if you need to. So the question I was asking is to suggest 2 reasons why the synthesis of carbohydrates is often challenging. So I came up with 5 points, and again I'll talk you through each of the 5 points that I came up with, but hopefully you've come up with these on your own. So I'll just delete my text box here so I can actually reveal the answers. And I'll try and explain to you why each of those is important, or why the difficulties or challenges are there. So carbohydrates are different or difficult in terms of when you want to make specific carbohydrates. You remember that actually small changes can change it from being a glucose to a galactose to alpha and beta with all the forms. So the difficulty often arises from the fact that we have lots of different hydroxyl groups on the same structure. And it's actually pretty difficult to choose to react at one particular hydroxyl group over another. So that's step number 1, that's a challenge in terms of we have these different hydroxyl groups, and it's very difficult to act at one particular group. This is where question or part 2 is, but it's saying it's difficult to bias which hydroxyl group will react first. They basically all have very similar reactivities, and you may be that I want to form this particular carbohydrate, and to do that I need to react at a particular carbon, or react at a particular hydroxyl group on a carbon, and therefore it's very difficult for you to specify which of those you're going to be acting at. So that's another challenge that we have to overcome. Now, to get that specificity at our hydroxyl groups, we often require what we call protecting group strategies to to mitigate this. So I think this would have been covered a little bit, but just to say, quite often what we would do first is that we'd react our hydroxyl group with something else to almost protect it from reacting in future. So we add bulky groups to this OH that will stop it from reacting with other groups. So we almost block it from reacting in future. That's not always that straightforward. It can be quite complex in terms of doing things like that, so it's not always the easiest thing, and requires obviously extra steps at that stage. Branch structures can form, so again, if we're acting at multiple OH groups or multiple hydroxyl groups, we can start to get branch structures being formed. It's very hard to limit where the reaction or where parts of the molecule are being added, so we can get very branch structures that we don't always want. And remember, we can get lots of different isomers being formed as well in terms of where positions of groups are, and we can't always designate the exact isomer that we want. We'll come to isomers probably in the second part of the workshop, but important just to say that isomers are going to be important here when we're trying to mix or pick specific carbohydrates. So hopefully you can understand those sort of key factors, but that's just to say why it's very difficult to synthesize specific carbohydrates, especially when looking at chemical synthesis, which is what we're dealing with potentially in that part of the question. Part B is looking at what the advantages and disadvantages of using enzymes to form carbohydrates in synthesis. So we don't necessarily just have to do it chemically, we can use enzymes to help us, but they have their pros and cons as well. So if I delete this box here to reveal the answers, advantage of enzymes is that they're much more specific, so we don't actually require these protecting group strategies to happen because our enzymes will work at a particular functional group in space. So we don't have to worry about protecting groups and that complexity in our mechanisms. Reactions should be carried out in aqueous environments, rather as obviously with lots of our chemical synthesis is going to be in potentially non-aqueous solvents. So again, looking in terms of environmentally friendly, if I spend environment properly. Oops, there we go. That's obviously going to help us in terms of making it a much cleaner process. We can obviously have now access to specific isomers, because again we can have specific enzymes that will produce specific isomers of our carbohydrate, because again enzymes are very specific to certain orientations, so they can make certain things happen. Generally a simpler purification, as we don't generally produce this mixture of isomers, so therefore we don't have to worry about long purifications to get rid of any of the sort of bits that we don't want. Now you might think, well, this seems perfect, we've got rid of lots of the problems that we've, or lots of the challenges that we've raised here, but unfortunately it's not quite that straightforward. If we go to some of our disadvantages, enzymes are generally expensive, okay, so this is going to be a much more expensive process than we'd used it chemically, and that can actually stop from going from maybe hundreds to thousands of pounds, and actually you might think that it's not viable to spend that amount of money to do these particular syntheses, so therefore you need to be a little bit careful in terms of that. So again, we can't use them for all because it is sometimes just too expensive to do on the scale that you want to do it. For some linkages that we might want, we might not even have a specific enzyme that's able to do that already, so we might not know about it, or we're not isolated yet, or they might just not be commercially available. So we don't always be able to form or have available enzymes to form all the different carbohydrates that we particularly want. Generally, it's all done on a much smaller scale. Chemical synthesis, we can do things in large batches, but generally enzymatically, because of the amount of reagents that we have, or amount of enzyme we have, is done on a much smaller scale than that, which again, if you look at industry, might be a good reason why we wouldn't want to use enzymes all the time. Due to the specificity of some enzymes, some structures might not be processed. So again, it's just saying that some enzymes are so specific that we're not able to form some of the other structures that we might want. So again, the specificity isn't always 100% useful in terms of what we want. Okay. So that brings us to a close in terms of the carbohydrate side of the workshop. So I will stop there for part 1. There'll be a part 2 where if I just scan down, we're looking at isomerism. So a bit of a recap for part 1, and I'll go through all the answers in terms of that part of the workshop. Hope this has been useful to you and you've been able to follow through the answers, and hopefully it will sort of aid you being able to do this on your own at home. Okay, so that's it from me for the moment. So good luck with the rest of the workshop. If you haven't done it already, you might want to have a go before you watch the second half of the video. Let me know any feedback in terms of if it's been useful or any bits that you want covering alongside in this sort of format. Okay, thanks, and that's bye from me then.